Okay, so after potential energy, we're going to talk about voltage. Voltage, unfortunately, actually have many names. So we know voltage by its definition from last year on electric circuits, right? So on electric circuit, we said that voltage is the amount of energy change carried by 1 coulombs of charge. So it could be protons or electrons or other stuff, right? Okay, so that's what we know about voltage from last year. But voltage is also called electric potential, not to confuse that with electric potential energy though. So electric potential energy is what we just did in the part 1 of the note. So potential, this is electric potential, energy. Okay, so electric potential energy is not the same as electric potential. So this is electric potential energy. Okay, so they're not the same. They're not the same. So voltage is either called voltage or electric potential. It can also be just called potential sometimes for short. And it's also called potential difference for short. And from last year, if you remember from the battery, it's also known as the electromotive force, EMF, right, from the battery last year. So for this lesson though, we'll be using the term electric potential or just potential or potential difference mostly. But if you have to understand what it is, it's really just voltage. It's the amount of energy carried by 1 coulombs of protons or electrons, 1 coulombs of charge. It's not a completely new quantity. Okay, so what is the equation for that? Now remember, what was the definition for voltage from last year? We just mentioned that. Is the amount of energy, right, carried by 1 coulombs of charge. So the amount of energy carried by 1 coulombs of electron. So if I have an equation for energy, if I only have an equation for electric energy, divide by charge and then that's it. Wait a second, we do have an equation for energy. We just have it from the last page, right? So take the potential energy equation and then divide it by 1 of the charge, and that's it. So let's divide that in here. So we take the energy equation. So voltage is defined as energy, the charge, right? So potential charge. In this case, the potential energy, Q1, Q2 over R, and then we are trying to divide it by a Q, right? 1 of the charge. So it's a charge 2. So the charge cancels out, and what happened? So what you have left is the potential energy equation, which is K, Q. Actually, if there's only one charge, then just Q over R, KQ over R. Okay, KQ over R, and that's it. That's the potential or voltage equation in electrostatic. Okay, so what does that potential number means now? And also in here, you notice that we are not adding that absolute value on the charge. That means we are going to keep the positive and negative sign. So what does the sign actually mean then? Okay, so the electric potential is defined in terms of the moving of a positive charge. Therefore, if we have a positive charge, it will always move toward the low potential area. So if you have an area that has high potential and an area with a low potential, a positive charge, like a proton, will always move to the low potential area. For example, in this situation, if you have a negative 10 volt or charge, so let's say you have a piece of metal that you can charge up. So one side, 2 pieces of metal, so like a metal plate, right? One side is charged with a negative 10 volt battery. The other side is charged with a positive 50 volt. So you can set it. So then what happened is if you had to put a positive charge in there, which way would the positive charge go? Positive charge always go toward the lower potential because it's positive. so it's attracted to the negative sign of the potential. So you always want to go toward the low potential. Whereas a negative charge, by the definition being negative, it will always go toward the high potential, which is the positive potential area, the positive voltage area. Okay, so positive charge moves toward the low potential, whereas negative charge moves toward the high potential. Okay, so move toward the higher or high potential. Okay, now, but sometimes it's very hard to say what is low potential and what is high potential. Maybe not really hard, but look at this one. Just look at this example. 100 volts and a 20 volts. Which way will the positive charge move toward? So which one is actually the higher potential or lower one? Positive charge goes to the lower potential. So positive charge will go here. So that 20 volt is actually like a negative potential in here, because it's negative compared to the 100 volts, which is on the other side. So it's a lower potential. It's not actually just positive and negative. You have to say which way is the lower one. So an electron, by definition, will go to the more higher potential, which is the 100 volt area. Okay, at this point, it's nice to actually have a summary of the 4 things that we have learned so far. Voltage. Okay, so what we have. So we start with the Coulomb's law, which is the electric force equation, which is KQ1 Q2 over R squared. And then you write the electric field equation here. The equation, just write down electric field, the heading for electric field, voltage, and write down the heading for potential. Okay, so do that. Now, it turns out that if you set them up in a chart like this, these 4 equations are actually related by this. Okay, you draw 2 arrows, one to the right. So to the right, you divide by Q. To go down, you multiply by R. Okay, so let's see how this equation, these 2 rules actually work. So if you want potential energy, for example, so you start with this one, and you want potential energy with the force, right? The force equation is what you started with because it actually looks very much like the gravity equation, which, you know, the structure of it you should actually memorize. So if you go down to potential energy, what do you need to do? You need to multiply by R. So when you take something that's divided by R squared and you multiply that by R, you get KQ1 Q2 over R. And that is exactly the equation that we need. And then, so let's say I want to start from there. Again, start from the energy, and I want to go to the electric field equation. So you look up here, if you want to go to the electric field equation, you need to divide by Q. So you have KQ and Q2. If I divide by Q, then one of the Q is gone. So it becomes KQ over R squared. Okay, so KQ over R squared. And that is the equation for electric field. Now you take the electric field one. Now you have 2 options. You either take the electric field equation or you take the potential energy equation, and you can go across. So if you take the potential energy equation, for example, you go across. So we already did that over here. Potential energy divided by charge equal to voltage. Voltage is the definition. The definition of voltage is the amount of energy carried by 1 coulombs of protons or electron, any kind of charge, right? Okay, so in this case, so one of the Q will be gone, but one of the R is already gone, so therefore KQ over R. Now, this is a nice summary for the 4 equations that we have in this chapter. And these 4 equations work with point charges. That means any charges that are acting like a point, like a proton, electron, or any larger particles, as long as they are like a charge on a point, then you can use these equations. There are situations where you cannot use these equations, and that will come later. So you look at this equation though, these 4 equations, the first 2 on the top are vectors. That means you will need to include direction with the answer, but because the plus or minus sign in the equation doesn't make any sense, you don't include the plus or minus sign. So you have absolute value on the charge 1, charge 2 on top. So you do need to include direction for force and electric field, but you're not using the plus or minus sign in your charges to tell you which way does it go. You use a diagram. In the bottom two equation, the potential energy and the voltage equation, these two equations, you don't need direction. These two are scalars. But you do need to use the plus or minus sign in your charge. So negative charge will give you a negative potential always. Okay, so you don't need direction, but you do need plus or minus on the bottom two equation. So I know it's a little counterintuitive. Okay, let's finish this up. Oh, the unit for voltage, I almost forgot. The unit for potential or voltage is volt. There you go. So shortcut is V. Okay, let's look at one example and then we're good. Okay, so calculate the potential at point P. Okay, so point P, and then there's a diagram. All right, so I guess I will have to go to that diagram first. Point P. Okay, point P is there. So we have three charges, 3 microcoulomb, 4 microcoulomb, negative 2 microcoulomb. So that one's negative. And then we have all this distance, right? 5 cm, 5 cm, 7 cm from the charge number 2. So this is labeling the charge. Charge 1, charge 2 is here, charge 3 is down here. So now how do we get the potential at P, at location P? Okay, so this is a lot unlike when we did our electric field, but because voltage is a scalar and energy is also a scalar, these kind of setup doesn't require you to do any vectors at all. It's a scalar, so you just add the numbers together. So for example, you do 3 of these. So the voltage at point P due to charge 1, the voltage at point B due to charge 2, and the voltage at point P due to charge 3. You literally just do all 3 of them and add the numbers together without worrying about vectors. So voltage and energies are not vectors. So even if you have like 3 objects like that, it's super easy. You just have to do the equation 3 times and add up the total. So it's almost like just adding money. So like someone in position 1 is giving you $10, in position 2 giving you $4, in position 3 take away $3. So how much money do you have overall? Okay, so I'll just add the 3 and the 10 and minus 4, right? So you don't have to worry about directions, just anything with scalar, right? Okay, so well, the angles are also not useful. So now let me go to this empty space. The program is lagging for no reason. And let me get the 3 equation. So voltage 1 is K charge 1 over R1. So K I'm not going to write anymore. Charge 1 is 3 microcoulomb. I can still see it from the edge of that screen. And the distance is 5 cm, which is 0.05 meter. I don't need to square, so that will be 1 numbers that I need to get at the end. So this is about 540,000. Yeah, 540,000. And then we have a voltage due to charge 2 that we need to do. So voltage due to charge 2. So voltage due to charge 2, so K Q2 over R2. So K, which is 9 times 10 to the negative 9. Q2, Q2 is 4 microcoulomb. Okay, I can still see it, kind of. So 4 microcoulomb over the distance is 7 cm. So here we go, 7 cm. And do that, 514,286. Okay, oh, the unit is volt and volt. Right, next one, the last one actually in this case, V3, this is charge, the voltage due to charge number 3. So K, charge number 3 is negative 2 microcoulomb. So we do use the negative, and then equation, we need the distance, which is 5 cm again, so 0.05 meter. And that will give us negative 360,000 volts. Okay, so no vector is necessary. All we have to do is to add up the numbers together. So the total voltage at point P is equal to V1 plus V2 plus V3 scalar addition. So it's literally just adding them. So if you do add the first two and then subtract by the last one, you get 694,286 vote is your total at the end. That's like way too many suffixes, but that's okay. Now, so just a final reminder, potential, just like voltage, is also a scalar quantity. So potentials are scalar quantities. So therefore, you don't have to worry about direction, but you have to worry about plus or minus sign. Just like money, no direction, but you can have plus or minus sign, right? So we do use the plus or minus sign on the charges. Okay, so that's it. I'll post the homework questions on the blog post. Thank you so much. Goodbye, everyone. See you next week.